Alright, so I will try to make something of this node A yet, I think. I'm going to start with the idea of a transpose. So if we have a matrix, m by n matrix, then the transpose is instead n by m. In particular, the jith element of the transpose is the ijth element of the matrix. And we say that A upper T is the transpose of A. Now here's an example. It's kind of a generic, numberless example, but an example nonetheless. So if I have this 3 by 2 matrix, then the transpose is this 2 by 3 matrix like that. The transpose of you see row 1 of the transpose is the transpose of the first column. So if I take this column and I transpose it, it becomes a row. And so that's the relation. The rows of the transpose are the transpose of the columns of the original matrix. Some basic properties of transpose is that the transpose of the transpose is back where you start again. And like I said, there's a connection between the rows of the transpose and the transpose of the columns of the matrix, like this. All right. To prove this is one of the first examples I have of a one of these index proofs. So you take A transpose transpose ij. All right, so by definition that's A transpose ji. All right, but then by the definition of transpose once more, we flip the indices aij. Okay, so A transpose transpose ij is equal to aij, and that's true for all I and j, where I ranges from 1 to m and j ranges from 1 to n. Therefore, it follows that A transpose transpose is just equal to A again. All right. That's a pretty typical proof. I'm going to show you a few more of those. I didn't get a chance to do them last class, but it's probably worth a minute or two of our time, especially since I can just point at them here. All right, so I defined this last time. The sum of a matrix is defined component-wise. The scalar multiple of a matrix is defined component-wise. So here's a theorem I didn't write down. I don't think I wrote it down last class anyway, but this is my proposition 2.26. And associativity of multiplication, associativity of addition, commutativity of addition, this distributive property for scalar multiplication. Here's another one, kind of an associativity of scalar multiplication by 1. Get you back where we started. Now, I think I've asked you one of these in the homework, I forget which one. Let's look at the proof of 1 just for a second, because it's pretty typical, the kind of proof you want to give. So if I want to prove that the sum of matrices is associative, what I do is I look at the ijth element of A plus B plus C, all right? Now, by definition, that would be A plus Bij plus Cij, all right? Unfolding the first addition, this one. Then, I use the definition of matrix addition again to change A plus Bij to Aij plus Bij. All right, so I just applied the definition again. Now, remember Aij, Bij, Cij, these are all elementary. These are arbitrary elements in a commutative ring. In particular, the addition is associative, right? So by the associativity of ring addition, I can add B and C first rather than A and B first, like that. Okay, and then I just kind of go back the way I started. I change this to B plus Cij by the definition of matrix addition, and then once more apply the definition of matrix addition to this matrix and this matrix to get that. Okay, but now I've showed that A plus B plus C is equal to A plus B plus C for all components, and it follows then that we have equality of these matrices. And that's a typical argument. That's one of the joys of the index notation, is it allows us to prove things about matrices without writing out a kabillion components. Like here's the proof of 5. So C1 times C2 A ij. So the first thing I do is definition of scalar multiplication is that you take the number, in this case C1, C2, and you multiply it by the component Aij. There it is. But then this is the multiplication of this number times that number in the ring. So by associativity of ring multiplication, I can rewrite it as the multiplication of C1 first, then by C2 and Aij. And then you just undo, again, the definition of the scalar multiplication of matrices. I can rewrite that as C1 times the matrix C2A ij, because that, by the way, is, all right, so. anyway, it's usually this is usually the deal. To get into the structure, you use the definition of the matrix operation. Then when you get down to the level of components, you typically use a ring property or later a field property. You make the necessary step, and then you go back by, again, using the definition of the matrix operations. That's very, very, very typical kind of proof. The zero matrix is a matrix of zeros. Okay, well, there. And here's a theorem about it. If you have 0 times any matrix, you get back the zero matrix. Okay, and this is, I guess this is matrix multiplication of the zero matrix times the matrix gives you back the zero matrix. If you add the zero matrix, you get back to the matrix. All right, I don't think these are especially exciting. I already told you guys a little bit, I think, about the standard basis, but let me reiterate again. So this is the, I can't remember, goodness gracious. It's been a long semester. Oh, wait a minute, I guess it hasn't. Anyway, the symbol delta ij is the Kronecker delta. This thing is 1 if I is equal to j, and it's 0 otherwise. So it's just a nice, simple symbol to capture that idea. Seems I was listening to the radio when I wrote this. Interesting. All right, so in particular, we use that Kronecker delta to define the standard basis. The jth component of EI is equal to like delta ij. So what that says is just that there's a 1 in the jth spot and there's a 0 elsewhere. Like here it is, E1 is this, E2 is that in a two-dimensional Cartesian product of the ring twice. Cartesian product of the ring 3 times, you get this 1 0 0 0 1 0 0 0 1, and then in the fourth Cartesian product of the ring, you got 1 0 0 0 0 1 0 0 0 0 1 0, and so forth, right? Now, it turns out that if you take any vector, any column vector in here, you can rewrite it as what's called a linear combination of these standard basis vectors. Like here's an example, 1 2 3. Can be rewritten as like 1 times E1 plus 2 times E2 plus 3 times E3. And that's actually a very important idea, this idea that we can build an object from a weighted sum of other objects. This is known as a linear combination. Here's a formal definition for you. This we'll be doing a lot of this semester. And ours is the commutative ring that we're thinking about here, all right? Our linear combination of objects A1 through AK, it's a finite sum, so we take C1 times A1 plus C2 times A2 plus plus CK times AK. In other words, a shorthand using our finite sum notation, sum I equals 1 to K of Ci AI. Okay, so this is an R linear combination where the coefficients are these C's, C1, C2, all the way out to CK. These form the coefficients of the linear combination. Now, down here I have a rather unenlightened proof that the every vector in the Cartesian product of the ring n-fold times is a linear combination of E1 through En. As you can see, what I do is I just kind of go, okay, so this is like V1, V2, Vn, so I just say, okay, well this is really the same as V1 with all zeros plus that. I think we can see that if you add component-wise, you get back to there. And then I just keep doing this. I guess formally speaking, perhaps I need an induction, but maybe I'm being lazy. Anyway, after a while, you see that you've got a Vn in every component here, you've got multiplication by V2 every component here, multiplication by V1, scalar multiplication by V1 every component here, and then you can pull out the V1, pull out the V2, pull out the Vn, like this. And there you go, V is V1E1 plus V2E2 plus plus Vn. And that shows you that every vector in Rn is a linear combination of E1 through En. Now, that said, it might be useful for me to stop and redo that. Let me just redo that just a second here with a different notation. Okay, so here's my claim. And I'm going to claim that if V is equal to V1, V2, Vn, then V is equal to a sum I equals 1 to N of Vi, Ei. All right? Now, to prove that my claim is true, all I have to do is show that this matrix and this matrix over here, which I'll shortly underline in orange, are equal. How do I do that? Well, I just need to show the components match, right? So on the one hand, I have Vj, right? And of course, Vj, by definition, is, well, I'm sorry, it's kind of hard to see this. Well, that the jth component of V is, yeah, here, fine. V, the jth component is Vj. You see that? All right. It's so simple, it's hard to understand. All right. But if I look at the jth component of this sum, right, then by definition of vector addition, and I suppose I should probably prove that if we can add two things, we can add n things. I suppose I never proved that. And we could prove that with an induction argument. It wouldn't be hard. Then, so what I have is I've got some I equals 1 to n of Vi, Ei, the jth element of that. Okay, that's just extending matrix addition to n-fold additions. All right, and then I can simplify this. What's the definition of scalar multiplication? Well, that's Vi times Ei, right? And the jth component of that. Now, so this is definition of scalar multiplication. All right. And then, well, we know the definition of the standard basis was that was Kronecker delta ij, right? Which means that this is 1 if I is equal to j and it's 0 otherwise. In other words, the only thing that matters is when I is equal to j, so we get Vj. And there you go, that completes the proof because we showed that the jth component of this equals the jth component of that, which shows you that they're equal, all right? So I think that's maybe a cleaner and maybe even less awkward proof than the one I give in the notes. You can take it or leave it. But there's another important kind of standard basis, and that's the one we can use to build matrices. So this Eij, E lower ij. Now here let me just squeeze in a little argument right here. So like for example, if I have A, B, C, D, I can rewrite that as A times 1, 0, 0, 0, plus B times 0, 1, 0, 0, plus C times 0, 0, 1, 0, plus D times 0, 0, 0, 1 in the 2 by 2 case, right? And that's exactly E11, this is E12, this is E21, and this is E22. All right, now I generalized that calculation down here in kind of the sort of lowbrow, clumsy way. Just write it all out and just look at it and apply the definitions component-wise, and there you have it. But golly, I do think the alternate proof is wiser. So what I do down here is I say, okay, here's a matrix, here's another matrix, B. I claim that they're equal. And so B basically has constructed this matrix A from a linear combination with the coefficients being the components of A, of these quote-unquote standard basis matrices Eij. So I look at BKL, excuse me, so that would be the KLth component of this, of how I've defined B to be this sum over the Ij's. And then I apply the definition of matrix addition and scalar multiplication to get this. And then the definition is that the Eij is only non-zero when I is equal to k and when j is equal to l, so that gives me Kronecker delta ik, Kronecker delta jl. That kills both of these sums and only leaves us with the one term which is non-zero, which is when I is equal to k and j is equal to l. There you go, akl. But if bkl is equal to akl, it follows that a is equal to b, and therefore any m by n matrix can be written as a linear combination of these standard basis matrices. So these things are important, and they're not that hard, but I know it's something new, so I just, we need to kind of come to terms with it. All right. Now I defined matrix multiplication last class for you guys, and so here we are And all right, let me get to where we worked out this, that the product of two matrices can be written as a bunch of dot products. We did that. And then, yes, Matthew, what do you want? You want me to load this? All right, just a second. All right, go shoot somebody. There you go. And then I have some examples. I hope you like the website I sent you a link to. I think it's pretty nice for seeing the mechanics of how these examples go, right? I mean, I suppose I could spend a class just multiplying matrices, but it would be pretty boring, and you'd probably learn more from just trying to multiply for yourself. One important aspect of those examples I just skipped over. Sorry. In fact, the last example is the one that's, I guess it's slightly preachy and important. Here I multiply a times b in 1, 2, 3, 4, and 5, 6, 7, 8, and I get 19, 22, 43, 50. On the other hand, I multiply b times a, 5, 6, 7, 8, 1, 2, 3, 4, and lo and behold, I get 23, 34, 31, 46. Well, I think you can see that these are not equal, right? So this goes to show you a very important thing about matrix multiplication, which is that we must be careful the order of the letters. You know, a product of two matrices in opposite order, they don't have to be equal even when they're defined. I mean, sometimes you might have like a 2 by 3 matrix times a 3 by 5 matrix. You couldn't even change the order of those because you wouldn't have the right matching of rows and columns in the other opposite order. For square matrices, you can always at least calculate the sum. Sorry, I have to load this. There we go. You can calculate the sum either order, but they may not be equal. That's because matrix multiplication is non-commutative. There's actually an interesting construction to quantify that failure to commute called the commutator. The commutator of two matrices is defined to be this bracket, comma AB. It's AB minus BA. Now, it turns out, I mean, obviously if the commutator of A and B is not equal to 0, that means that AB is not equal to BA. And it's actually a very interesting thing. This is an example of what's called a, it's not Lie, it's a Lie bracket. Nothing to do with statistics. It's of fundamental importance to quantum mechanics. I mean, it turns out that if you have two operators which are represented by matrices, if those matrices commute, then you can measure both of those physical quantities simultaneously to like arbitrary precision. On the other hand, if the operators which represent those physical quantities don't commute, then there's this uncertainty. You know, you can't simultaneously measure both of them with complete precision. For example, momentum and position operators don't commute, and that's the source of this famed Heisenberg uncertainty principle. But anyway, I digress, obviously. All right, so theorem 2.3.11 is an important theorem. Basically, it says, hey, you can multiply matrices and do scalar multiplication of matrices, and multiplication and addition of matrices behaves just as you'd like it to, but be careful to keep the order of letters the same, all right, because we just learned that matrix multiplication doesn't commute. All right, great. Now, I think I asked you to prove one of these yourself. I have the proof of, let's see here, 3 down here. Let's look at that for a second. The proof of 3. So what you do to prove 3 is you look at the ijth component of the left-hand side. And then I apply the definition of matrix multiplication. So the definition of matrix multiplication says that I have aik times x plus y kj. All right. Now technically I didn't write it down, but the sum over k goes from what? Well, a is m by n, and x and y are n by p. So that sum over k actually goes from 1 to n, as in nanu, if you're interested. Now, then you have, to break this up, I use the definition of matrix addition, which is done component-wise, right? At this point, we have a sum of real number products, and so I can use property, excuse me, I'm trying not to keep it real. I'm trying to keep it a ring. There's no saying. I'm sorry. I guess if you like it, you can put a ring on it or something. I don't know. There's really not many good ring sayings. But oh wait a minute. One ring. There's something interesting about a ring. It seems to me. But, oh yes, it has to do with. think mostly it has to do with this little guy. But let's see here, I'll put him here to remind me it's a ring. So this is xkj plus ykj, and then I multiply because we have distributive property for rings. Real numbers. No, no. Rings. Commutative rings. All right, fine. Anyway, and then property of finite sums. I think I actually proved this one in class. So the sum of a sum is the sum of the sums. No, it's the sum of the, I don't know. Anyway, it's a property of finite sums. I can break this up like so. And an erroneous. This is a it's a bonus parentheses. You can delete that one. Sorry about that. And then I again use the definition of matrix multiplication to say the k, summative over k. So that's axij. This is ayij. And then definition of matrix addition once more, and there's ax plus ayij. Aha! Well, we've proved this is equal to that for arbitrary ij, and then it follows that a times x plus y is equal to ax plus ay as a matrix equation. So to prove the other ones, it'd be much the same. For example, I think I asked you to prove number 1. So like number 1, I would start with something like this. I'm asked to, prove the associativity matrix addition, right? So I've got ax times z. And so I put some parentheses out here. I look at the ijth element, right? And so I would start with saying, okay, so that's the sum over, let's say, k of ax ik zk j. All right? And then I'm going to have to unravel that, right? So this is going to be sum over k. That's another sum over L, and that would be A I L X L K. Now be careful. There's parentheses here, right? And all that's times zkj, right? Now, property of finite sums says that I can rewrite this as a sum over k, sum over L of A I L X L K, let's say parentheses, zkj, right? And then, well, you go from there. But basically, at the next step, you're going to use the associativity of ring multiplication to move the parentheses over here, and then you just kind of unfold the steps in the reverse order. All right, so it's kind of like the proof I showed you in the notes, but and the proofs of the other things in the theorem are similar. All right. That brings us to some deeper properties of the transpose. We already proved that the transpose of the matrix again. I've asked you to prove that AB transpose is B transpose A transpose in your homework, and you can pull a scalar out of the transpose, and the transpose of the sum is the sum of the transpose. So let's look at the proof of 4. By the way to do this is much like I just did. I'll get you started to prove number 2. Like the start of this proof, I would just say, okay, so A, B, transpose, ij is equal to, well, A, B, parentheses, ji, right? And then what do? I go, okay, well, I can't write anymore, but I mean, that's where you go. Fine, I'll write one more step since you're watching this. Sum over k of A, jk, bki, all right? And then, okay, but then you want to somehow work over to the right-hand side, which has B transpose and A transpose, right? So you have to think through that, but this is how you start. It's not that hard, but it's very hard if you don't use index notation. Now, down here, here's the proof of actually 3 and 4 at the same time. This is an important trick. So if I look at the A plus C times B transpose ij, well, that's A plus C B ji by definition of transpose, right? But then, by the definition of matrix addition and scalar multiplication, see, I'm being lazy. I should have written that in here somewhere. That's AJI plus C times BJI. All right, so I'm using, to get from here to here, definition of matrix addition and scalar multiplication. This proof would be improved if I'd written that like here or something. All right. And then I undo it by going, okay, so that's A transpose ij, and then this is C times B transpose ij as well. And but you have this is equal to that for arbitrary ij, so it follows that we have A plus CB is equal to, A plus CB parentheses transpose is equal to A transpose plus CB parentheses transpose. And then you can just look at special cases, like look at A equals to 0 to get the CB transpose is equal to, see that shouldn't, the C shouldn't be in there. I'm sorry, this isn't quite right. This there should be a parenthesis. The parenthesis should be like here. Sorry about that. It should be C times B transpose there. Point is, you can pull the C out. And so if you look at A equals to 0, it gives you the third one, but with A replaced with B, no big deal. And then if you look at C equals to 1, it gives you 4. It's not, this could be improved a little bit. Sorry about that. All right. So let's move along here. I'm actually working on battery power. I left my adapter at school, so this will have to be short. Here's an interesting pair of numerical examples. I look at AV, and I get 1943. I look at AW, and I get 2250. All right. Then what I do is I take this matrix, this vector 5, 7, and this vector 5, 6, 8, and I put them in a concatenate them, glue them together into a matrix 5, 6, 7, 8 like that. And when I multiply 1, 2, 3, 4, I get 19, 22, 43, 50. But that's exactly the same thing as I got before the 1943 and the 2250 just glued together. So this shows you a pattern in particular that for B equals to VW, I glued V and W together, right? So if I look at A times VW, what happened is I was able to kind of move the A inside. So A times V concatenated with W was really AV concatenated with AW. This isn't an example, is not an accident of these numbers. This is actually a general property. I refer to it as the column, the concatenation proposition for columns. I think I asked you to prove that in the homework. So here it is. You've got an M by N matrix A. You've got an N by P matrix B, so they're multipliable. And you can break B up into columns, column 1, column 2, column P. Then A times B actually can be rewritten as A times column 1, A times column 2, concatenated with A times column B. To prove this, what you want to do basically is just take the ijth component of this and see why it must be the same as what you have over here. I guess it might be easier to start with the right-hand side here. I don't know. This isn't a terribly hard thing to prove, but you must understand the notation of the indices. Otherwise, it is hard if you don't know the indices, what they mean. But the proof of this shouldn't be more than maybe three or four lines. If you're trying to see it by actually multiplying things out, that you're not doing it the right way. Now, once you know this, you can prove a corresponding thing for rows using properties of transposition. And here it goes. If I have A times B, and so I take A and chop it into rows, then so A times B, which would be like this times B, right? It turns out that it's the same as multiplying on the right each row of A by B. So to prove this, I'm tired of writing row 1 and row 2 of A, so I just write R sub I for the rows of A. So the transpose of A is formed from transpose of row 1 concatenated with transpose of row 2 all the way out to the transpose of row M. And then I can multiply B transpose times A transpose using the column concatenation, which said that I can move a matrix multiplication of the column concatenation, the matrix divided up into columns, right? I can move the B transpose out here into multiplying each one separately, so like that, B transpose R one transpose. This is just the proposition 2.3.14 applied to this. So I move the B transpose in, here, 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 and here. But of course, B transpose A transpose transpose is equal to, by socks shoes principle, which you'll prove in homework, and I got you started on about 3 minutes ago here, is A transpose transpose B transpose transpose, because they switch order and transpose, and but that's A and that's AB. Okay, so if I take the star of transpose, on this side I get AB, on the other side I get the transpose of this, right? But what that does is it makes columns into rows, right? So column 1 becomes row 1, column 2 becomes row 2, column n becomes, I should say more carefully, the transpose of the mth column becomes the mth row. And so then, yet again, applying sock shoes, I get R1 transpose transpose, which is just R1, B transpose transpose, which is B, and so forth in each one. And there you have it, R1B, R2B, RMB, which is exactly what I have up here. And so there's the concatenation proposition for rows. Another way we can look at matrix multiplication is just as a sum of outer products. If I have A times B, I can actually write it as column 1 of A times row 1 of B, column 2 of A times row 2 of B, all the way out to column n times row n of B. It's kind of a weird idea, isn't it? Let me, if I have enough battery life, debatable. Uh-oh, I'm in the red. I best make a, well, tell you what, I'm just gonna cut it off here, and hopefully I'll figure out how to take videos with my phone.